Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience. Hi everyone, today we have with us Thorsten Feichtner, who is the Managing Director of the Excellence Cluster at the University of Würzburg. And the Excellence Cluster is called CTQMAT. Hi Thorsten, welcome to Meet the Curator podcast.
Hi Pranoti, thanks for inviting me.
All right, let's begin. So let's start with your history in coming to the current research field. How did you end up in your current research field?
Yeah, so the way to work in nano-optics was not straightforward. So I did study in Würzburg, and I studied with a goal to, of course, save the world. Yeah, so I wanted to go into the research field of plasma physics and build a fusion reactor in the end. Mm-hmm. But Würzburg is not the best place to do so. And while studying, I really got hooked on the idea to research about spintronics. So spintronics is maybe the future of computing, and it's of course a topic of the Excellence Cluster. But when I applied for a diploma thesis project, all of the groups were full. So I was promised when I wait 9 months or so, then I could get a project, but no student wants to wait so long. So I had to take a look around, and then at the time, Professor Bert Hecht just started his working group at the University of Würzburg, and he is quite famous for working on nano antennas. So he, in principle, has the first science paper introducing the concept of nano antennas, and I talked to him, and he was building up a work group, and suddenly I was a diploma student in a group of 4, and doing, in the first year I did only numerical simulations to get more or less the toolbox to predict antenna behavior running, and that's how I got into the topic. After this year, the group was awesome, and the research topic was super interesting. So when I was offered a PhD position, of course I stayed, and yeah, that's it. So I came to the field of nano optics and optical antennas.
And then you stayed in the field.
Yes, I stayed.
Okay, wonderful. So could you paint us a picture? So where does the field of nano antennas or your current research fit in this big picture of materials or nanoscience? Where does it fall?
Okay, the name itself says it's nano. But nano antennas are quite small because light has a wavelength of a few hundred nanometers. So from deducing it from classical antenna theory, nano antennas should also be as long. This is somehow true. So a normal nano antenna is about 100 nanometer long and 10 nanometers thick, and then resonant at visible light. And of course, it's a material issue because you have to learn how to structure a metal that it is becoming a rod. So there are different ways to do so, which I will introduce in the Twitter account. But it is, of course, learning how to make complex geometries with scales down to 10 nanometer in gold or other metals. And then these nano antennas are also possible building blocks of the famous metamaterials, which are large volume but nanostructured materials which can bend light. And maybe one of the famous topics is the cloaking cap, which has been built for single wavelengths already with these metamaterials.
Okay. Interesting. That's super interesting. I love the part where you mentioned the bending of the light. That kind of explains what you exactly do. So it sounds like you do a lot of interesting research projects or experiments in the lab. If you had to pick one, could you pick your favorite or the most adventurous one and explain it to us in super simple words?
Okay, I can try. So everybody knows about the artificial intelligence topics which are popping up everywhere, and
Right.
everybody is using more or less some neural network or something like that. Yeah?
Right.
But already some years ago, I tried to apply an artificial intelligence algorithm called evolutionary optimization to optical antennas. So I gave some constraints to the geometry of an antenna, but also some freedoms. And this algorithm should optimize it for light focusing. So making the light spot in the center of the antenna as small and strong as possible by when it's illuminated. And this
Right.
worked out wonderfully. And the geometrical constraints which I implemented in the algorithm were so that it could be fabricated directly from the numerical result with a focused ion beam machine. So I just took the result, had a script which told the focused ion beam machine how to make this geometry out of real gold, and then these antennae worked. And this was a crazy combination of artificial intelligence with nanostructuring and light focusing. So was really a super nice project, especially as in the end I was able to learn why these antennas, which were of no shape ever seen before, are better than the classical antennas which were used before that.
That's really cool. And does it still work if you run that algorithm today? Will it still make the antennas of your desire, so to say?
So to be true, this artificial intelligence will get always to slightly different results because it's not brute force. It's just something about learning how the geometry should look like, and
Right.
it's similar, but it works. Yes, and of course I'm now working on applying this to other topics. So especially for nonlinear light generation.
Okay. That sounds super cool. That's a crazy crossover of the sci-fi meeting the materials and nanoscience. So this is a really nice example, so to say.
Yes, it is. So I'm really very happy with the outcome of this project. Yes.
Okay, wonderful. Cool. So I hope that your research experience so far has been wonderful and super exciting. Having said that, if you had to choose, if you had three wishes to improve the research experience for you or for the whole scientific community, what would you ask for? Not promising anything, okay?
I won't promise anything, of course, but right now I'm in the field of science administration. So this is my main job. I'm doing research, of course, next to it, but my bread and butter job is more or less helping scientists do science. And this is also something which I would wish for all the scientists. A lot of professors or postdocs are losing a lot of time by filling forms, by getting to know how some law is working out for their cases, and so on and so forth. And this is something which really slows down research. And if this could be improved, if this would be one of my three wishes, and the job description of a science manager is something which is quite new and which is just being established here in Germany, and it's a little bit more established in the US, for example. And this is something which I'm really looking forward to, that this increases, so that the scientists can do more awesome science and less paperwork.
That's
Then, yeah, that's number one.
yeah.
So it is not ranked, yeah, but this is what came to my mind first.
Right.
Next very fundamental thing is the publication pressure. So everybody knows publish or perish. If you don't have your 2 high impact publications per year, then you are lost and you cannot stay in science. And this is something which I really, really have. Yeah, it's really a high pressure on every scientist to be forced to publish. It's I think I don't have to tell anyone that if you want to publish 2 papers a year, then you make safe research. Yeah? You make small steps in a direction which you can anticipate the results, and you are not doing the high risk research projects which might have 2 years of no scientific outcome and then maybe a negative result, which is also important, but nobody will publish it. So this is also something which I would like to change, because this development is right now going in the wrong direction, in my opinion. But I have no good solution, to be true, because everybody wants to have some numbers to be ranked, and publications are the number.
True.
Yeah, and third, I would like to have a little bit more public support even. And with public support, I mean different things. So view number 1 might be the fake news discussion, which is right now boiling high in the context of climate change. And there are much more people are telling, oh, scientists don't know what they do. Scientists try to push people into a meaning and so on and so forth. This is something which scares me, I have to confess. And the next thing is that view number 2 of more public support would be that more tax money would be spent to support science. Because there is always this magic number of about 3% of a country's income which should be spent into research, at least to be a good research country, but the number is still quite small. And we have so many big problems to tackle, and good researchers which have no funding after a few years in science. So money could be spent for science much more, and it would be worth it.
Okay, yeah, all 3 are fair wishes, and I completely agree with all 3 of them. The admin pressure, so much time spent in the admin, and then the rather like quantification or checking how the scientist is performing, so to say, where the scientist is standing. We definitely have to rethink and remodel that. Not go beyond the H index or impact factor and so on and so forth. And also with the funding, I completely agree that science is fun, and it brings so many if you invest money in science, the discoveries benefit the society as well. So it makes sense to do it. To put it simply, like in super simple words, I absolutely agree. I wish I could grant those, and just with a flick of my fingers, I could just change it and make it happen. But I can't. But I hope we are working towards it, going in the right direction, so to say.
Yeah. So at least telling people that they hopefully make up their mind.
Yeah, absolutely. We are raising the voice, and we are putting it out there. That's the first step, I guess, and then the change will happen slowly. Okay, cool. So could you tell us what are you most looking forward to in the 3 months?
So the next 3 months will be what will be there? Christmas. Will be fun. But it's true.
Christmas market.
Some mulled wine will be also fine. But research-wise, the next 3 months are not sufficient. But in May, I have an awesome opportunity, because I will start my Marie Curie individual action in Milano.
Ooh.
And I got my proposal granted, and I will move for 18 months to the Politecnico in Milano, and I will do some a really cool project about super short laser pulses exciting nonlinear antennas and hopefully enable some optical switching. And this will be a great opportunity because I will change environment. This is always a nice thing because you learn a lot of new people, a lot of new methods, and you always thrive when you change environment. So, and of course, this is a very important step in my scientific career because I will therefore also be abroad finally. And the great goal for me is, of course, becoming one day professor. And being abroad is a crucial step in this. And of course, I can work together with people which I already know, and it will be a blast. I'm really looking forward to this.
Yeah, it sounds amazing. And maybe you can next year in the second half of 2020, then you can curate the account again and tell us or update us what's going on as a traveling scientist, so to say, or visiting scientist, visiting researcher in a different country, what you've learned, what changed, and how you adapted. That would be cool.
That's a cool idea, yeah.
Okay, all right. Then before we let you go, could you explain or could you tell us what are the challenges, the big challenges faced by the field of materials and nanoscience in general? What are the questions the researchers are working towards
So
answering?
from the research point of view, a lot of research is now going to control the quantum nature of matter. So all the constituents of any made-up artificial nanomatter is going so small that it can only be described, of course, by quantum. And this is also true by for the nano optics case. Yeah, so gaps in nano antennas are becoming so small that electrons start to tunnel. And making use of this and understanding this is one of the great tasks in our research area.
Right.
This is for the research case, but for societal questions, there's also the task to find out how to make the results of our research useful. And one problem is that all of the methods that we use are super slow or super expensive or both. And this means that when something works and something has an obvious, super nice application, then it still might take 40, 50 years until it's on the market. This is one thing.
Right.
And this can be slowed down because often it's not clear if the material is hazardous in any way. So there might be the discussion about the titanium or silver oxide nanoparticles in sun blockers also, or of how the carbon nanotubes are harming the lungs if you breathe them. So these are all the questions which fundamental science doesn't want to tackle.
Right.
Because it's not interesting in the research topic they are going into, but it's very important for making them market available.
Okay.
So these are, in my opinion, two of the
Big
biggest
questions.
big questions.
Okay. Well, I hope we are working towards it. And by we, I mean the funding agencies, the researchers, everyone is working towards tackling these challenges. Well, thank you very much, Thorsten, for speaking with us. It was really nice to speak with you. And I think I personally learned quite a bit.
Thank you. Thank you, too, for giving me the opportunity. And yes, I'm looking forward to telling the world about the research I'm performing.
That's wonderful. We look forward to having you on the Twitter account.
Thanks a lot.
Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.